Yeah, good evening to all. It is Navneet Krishnan from iitiansgateclasses. In this class, we'll be seeing GATE 2017 flight performance problems. A total of 10 marks has been asked in this from flight performance. Okay, we'll see one by one. GATE 2017 question number 6. Which one of the following statements is not true? Option A, pitching moment of any aerofoil at any angle of attack is always zero at the center of pressure. Option B, the pitching moment of any aerofoil at any angle of attack is always zero at the aerodynamic center. Option C, the center of pressure and aerodynamic center coincide for a symmetrical aerofoil. Option D, the pitching moment about the aerodynamic center for any aerofoil does not vary with respect to angle of attack. Okay. So, if you see this question, first option A you'll see. The pitching moment of any aerofoil at any angle of attack is always zero about center of pressure. That is the definition of center of pressure. Okay, center of pressure means pitching moment about that arrow, about that point is zero. That is the definition of center of pressure. So option A is true. Option B, pitching moment of any aerofoil at any angle of attack is always zero at the aerodynamic center. The definition of aerodynamic center is pitching moment of aerodynamic center is constant. It doesn't change with respect to angle of attack or Cm. Cm is constant about aerodynamic center. Dou Cm by dou alpha is equal to 0. Dou Cm by dou alpha or dou Cm by dou Cl is equal to 0. So it doesn't vary with respect to any angle of attack or Cl. Is the definition of aerodynamic center. So option B is false. Option C, if you see, center of pressure and aerodynamic center coincides for a symmetrical aerofoil. If you see at zero angle of attack, there is zero lift. The pressure distribution is uniform throughout. So the center of pressure and aerodynamic center remains constant. Okay. There is no moment about that point. So there is no shifting of point is required for a symmetrical aerofoil. So option C is also true. Option D, the pitching moment about aerodynamic center for any aerofoil does not vary with respect to angle of attack. Yeah, it is constant and doesn't vary with respect to angle of attack. Is the definition of aerodynamic center. So option D is also true. So only option which is not true is option B. So option B is the correct answer. Okay. GATE 2017 question number 7. Which one of the following statements is not true? Option A, compared to laminar boundary layer, turbulent boundary layer is more desirable on a wing operating at large angle of attack. Option B, the skin friction drag of a turbulent boundary layer is larger than that of a laminar boundary layer. Option C, the location of transition from laminar to turbulent boundary layer depends only on operating Reynolds number. Option D, the separated flow doesn't lead to a turbulent boundary layer. See, this question is generally related to aerodynamics, but still they have talked about skin friction drag, so I want to explain what it is. Okay. If you see on wing at large angle of attack, if the wing is kept at large angle of attack, then to overcome the flow to overcome that large curvature requires lot of energy. So they spend lot of energy in transition. So after a certain point, the flow gets separated. So what happens? It loses its energy, so it gets separated. If there is a laminar flow, the flow is having less energy, so it gets separated easily. If it is a turbulent flow, it is hard to separate the flow because it has got lot of energy. So that's why a golf ball which has lot of dimples. So what happens? The dimples make sure that there is a transition from laminar to turbulent. So if there is a turbulent flow, that golf ball can travel a longer distance. So this is why we use same for aircraft also. We have a vortex generator, so which generates which transition which makes the transition from laminar to turbulent. Thereby, flow will get attached to the surface for a longer time, so it is more desirable. So option A is true. Option B, skin friction drag for a turbulent boundary layer is larger than laminar boundary layer. Yes, because turbulent boundary layer is having a lot of surface friction. So there is a lot of shear stress. That means it causes more skin friction drag. Okay. Lot of energy, so lot of skin friction, thereby lot of skin friction drag. Okay. So this is also true. We'll come back to this option. Option D. A separated flow does not necessarily lead to a turbulent boundary layer. A separated flow can be a turbulent boundary layer or laminar boundary layer. It doesn't need to be only turbulent boundary layer. Okay. Any boundary layer can get separated if there is no energy to the flow. Okay. That is, velocity gradient becomes negative or pressure gradient becomes positive. Any boundary layer can be separated. So this is false. Does not necessarily. Sorry, this is also true because it need not to be turbulent boundary layer alone. It can be laminar boundary layer also. Now we'll see what happens to this. Location of transition from laminar to turbulent boundary layer does not depends upon Reynolds number alone. Why? Because it also depends upon the velocity profile. It depends upon the displacement boundary layer thickness. Because boundary layer thickness depends upon the velocity profile. The velocity profile depends upon the surface friction and the geometry. So if you know only the geometry, flat plate will have a different boundary layer and aerofoil will have a different boundary layer. For example, flat plate placed in this manner will have a different boundary layer. Flat plate placed in this form will have a different boundary layer. If you have a streamlined body like aerofoil, will have a different boundary layer. So it depends upon the geometry and the surface friction. The surface friction. So the surface friction ensures that there is a different velocity profile on the body. When there is a different velocity profile, then there is a different displacement thickness, boundary layer thickness. Thereby, the location of transition from laminar to turbulent depends upon the surface friction, geometry, and Reynolds number. In turn, depends upon the velocity profile. Okay, so it is only the false. It not only depends upon Reynolds number, it depends upon various parameters also. The location, okay, where it is transforming from laminar to turbulent. Okay. Next. Question number 31. Consider a straight wing with rectangular platform of aspect ratio 10 with NACA 0012 aerofoil. That means it is a symmetrical aerofoil. So the span effectiveness factor for this wing is 0.95. Assume the flow to be incompressible and governed by thin aerofoil theory. The lift coefficient of this wing at an angle of attack of 6 degrees is dash in 3 decimal places. If you see, they are given a symmetrical airfoil. For a symmetrical airfoil, CL versus alpha is like this. So lift coefficient at zero angle of attack is 0. So CL can be written as CL for this wing can be written as AW into alpha W. The lift curve slope into alpha. Now we have to find out what is the lift curve slope of the wing. What is the lift curve slope of the wing? It's nothing but lift curve slope of the aerofoil, where A0 is the lift curve slope of the aerofoil. If it is in per radian, if AW and A0 is in per radian, we can use this relation. According to thin aerofoil theory, A0 for any aerofoil can be written as 2 pi per radian. So if I substitute 2 pi per radian, E, they given it as 0.95. Aspect ratio, they given it as 10. Substituting that, I get lift curve slope as 5.1905 per radian. 5.1905 per radian. Now, if I have to find out what is CLW, it is AW into alpha W. Provided that I have to change alpha into degree, alpha into radian, or AW into per degree. So it is 5.1905 per radian. Alpha of the wing, they are given it as 6 degree angle of attack. So into 6, if I have to convert this in radian, multiply it by pi by 180. So I get the answer as 0.5435. They asked us to round off to 3 decimal places. So when I am rounding off to 3 decimal places, it is 0.543. Or 544 can be written. 543 or 544. Any doubt? Next question. Question number 39. A pilot was flying a single engine propeller aircraft maintaining a steady level flight at a lift coefficient CL equal to 0.5 at an altitude of 500 meters. Due to some emergency, at the same altitude, 500 meters, pilot has fully deployed the landing gear. If the pilot wants to maintain steady level flight at the same CL and at the same altitude, which one of the following control actions should the pilot undertake? Option A, move the elevator up and decrease the throttle. Option B, move the elevator up and increase the throttle. Option C, move the elevator down and decrease the throttle. Option D, move the elevator down and increase the throttle. If you see, initially there was lift equal to weight, thrust equal to drag, because they were maintaining steady level flight. Now, suddenly, the pilot has, consider this is the airplane, pilot has deployed the landing leg. Okay. Pilot has deployed the landing leg. When he has deployed the landing leg, what happens? There is an increased drag. There is an increased drag because flow is affected by the landing gear. So there is an increased drag. If there is an increased drag, drag is increased. If there is an increased drag, then to overcome that increased drag, if the pilot has to maintain steady level flight, thrust has to be increased. So thrust produced by the engine has to be increased. Okay. So thrust produced by the has to be increased. So if thrust has to increase, they have pilot has to increase the throttle. Thrust has to be increased. Pilot has to increase the throttle. Not only that, that increased drag occurs a point below the CG. This is CG axis. Somewhere here is the CG axis. That the increased drag acts below the CG axis. So this creates a nose down moment. About CG, it creates a nose down moment. If the pilot, there is a nose down moment and the pilot has to maintain steady level flight, means what he has to do? Pilot has to do? Pilot has to deploy the elevator to overcome that nose down moment. So pilot has to deflect the elevator upward like this. When it's deflecting the elevator upward, it creates a negative lift. Okay. This lift in the downward direction because there is a negative camber over here. So it creates a negative lift. CG is somewhere here. So it creates a nose up pitching moment for the aircraft. So deflecting the elevator upward and increasing the throttle or increasing the thrust can maintain steady level flight if the landing gear is deployed also. So only option correct is move the elevator up and increase the throttle. So option B is the correct answer. Okay. Any doubt? Next. Question number 40. A conventional low-speed aircraft has the following aerodynamic characteristics. CD naught equal to 0.02, E equal to 1. The aircraft was flown to maintain a steady level flight and for a minimum thrust required, lift coefficient of CL equal to 0.8. The numerical value of the aspect ratio of the wing is dash in 3 decimal places. They are given the condition, it is minimum thrust required. Thrust required minimum is nothing but drag minimum condition. Drag minimum condition is nothing but CD naught equal to CDI. CD naught equal to CDI. CDI can be written as KCL square. K can be written as 1 by pi ER into CL square. So it is CD naught equal to CL square by pi AR. CD naught is given as 0.02. E is given as 1. 0.02, that is equal to E is 1. Aspect ratio we have to find out. The lift coefficient they are given it as 0.8. Only unknown is aspect ratio. From this we get aspect ratio as 0.54. Sorry, aspect ratio as 10.186. Round up to 3 decimal places, it is 10.186. The answer is 10.186. Any doubt? Next. Question number 43. 8/2017. Question number 43. An aircraft is to be designed to ensure it has enough excess power to achieve steady climb at a flight path angle of gamma equal to 10 degree. Maintaining CL by CD equal to 10, the numerical value of thrust to weight ratio of the complete aircraft to meet the above requirement under standard atmospheric condition will be dash in 3 decimal places. For climbing flight, they have told it is climbing. For climbing flight, we know that lift is nothing but W cos gamma. Thrust is nothing but drag plus W sin gamma. So I am taking weight on the other side. So it will become thrust by weight, that is equal to drag by weight plus sin gamma. From this equation, first equation, I can rewrite it as weight can be written as lift by cos gamma. Weight can be written as lift by cos gamma. Substitute it here. So my equation will become thrust by weight equal to drag divided by weight is written as lift by cos gamma plus sin gamma. Okay, plus sin gamma. This cos gamma can be taken 1 by cos gamma can be written as cos gamma. This drag by lift can be written as 1 by L by D plus sin gamma. The angle, flight path angle, they have told gamma equal to 10 degree and CL by CD is also 10. So L by D can be written as CL by CD. So it is cos 10 divided by 10 plus sin 10. We get that answer as 0.272. By round off to 3 decimal places, it is 0.272. Any doubt? If you have any doubt, you can ask. Otherwise, we'll wind up today's section. Okay. Yes, Vasant. You have some doubt? Clear? Thank you. Good night. Thank you.